Hi, and welcome to this coding demo. This is coming out of the Focus on Fundamentals for Programming with C. I'm going to be covering Chapter 5 by writing code, so I will click on the new repl.it and say a new C project here. And again, this is coming out of Chapter 5. And starts on page 110. So that's the book by Dr. Stegman, The Focus on Fundamentals of Programming with C. And this chapter 5, the title of it is Number Systems. So number systems. So the first thing we're going to talk about is using decimal numbers. In fact, I'll put a title here, say Chapter 5 on number systems. I recommend you follow along as we're going through this lesson so you can see things as we go through them. So in the book they have, for example, a number, a base 10 number, looks like 739. So 739, base 10 number. And of course, base 10 is what you're all familiar with. We have 10 fingers. So if we have 10 fingers, you have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Those are the base 10 has 10 digits, and there they are. And in fact, if we said printf and we said num is %d \n, and we print out the value of num, if I click and run that, no surprise, it is 739. But when you look at what that really means, it really means taking the value of 9 and multiplying it by 10 raised to the 1 power. Now I'll actually to the 0 power, so I'll do it like that. So that would actually give us the value of 9, because 10 to the 0 is 1. So 10 to the 0 is 1. And then we would take the second digit, the 3. We'd say, well, 3, since that's in the next position, that would be 10 raised to the 1. And 10 raised to the 1 is 10. So 10 times 3, we would get 30. And then, of course, this last digit, the 7 times 10 raised to the 2, because it's at position 2, that is 0, 1, 2. And of course, that would be 7 times 100, because 10 raised to the 2 is 100, so that would give us 700. And if we added all those up, right, 739, the total would be 739. And of course, everybody knows that. That's not an issue. But the reason I wanted to begin with that is because we also, in computer work, deal with binary, which is base 2. So unlike base 10, where we had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, base 2, we have 0 and 1. How you like that? Just 0 and 1. So if I have a number then, given that I just have a 0 and 1, and if I start counting based on that, let's say I have a number, let's say I have a number 1010 in binary. Okay, so if I have that in binary, well, we can do the same thing that we did here with this number. We basically start with the least significant digit, which is a 0. So we'd say 0 times, instead of saying 2 to the 0, instead of saying 10 to the 0, we would say 2 to the 0, which would be 1, but of course 0 times 1 would be 0. And then I'd take the next digit, so right here we have a 1, so that would be 1 times 2 raised to the 1 power, which would be 2, so that would give us 2. And then the next digit, we have a 0 right here, so we'd say 0 raised to 2 to the 2 power. Well, 2 to the 2 is 4, but 0, so we get 0 out of that. And then the last one, we have a digit here, a 1, so we'd say 1 times 2 raised to the 3 power. Well, 2 raised to the 3 power is 8. And so then we would take all of those, and to find our total, we add them up. And so the total would equal 8 plus 2 would be 10 in decimal. So 1010 in binary is actually 10 in decimal. So that's the base 2. And another one we use pretty often is a hex for hexadecimal, which is base 16. And just like the others, that means we have 16 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But wait a minute, we need some more digits, A, B, C, D, E, F. So those are our 16 digits that we have by using base 16. So as an example of this, let's suppose I had a number, say, how about 1, 2 in hex, and the convention is you put 0x in front of a hex number. Well, using the same process we use for base 10, the same process we use for base 2, we'll do the same thing here. We would take the lowest digit, the 2, and multiply it by 16 raised to the 0 power. So that would give us 2, right? Because 16 to the 0 is going to be 1. And then with the next digit, 1, would be times 16 raised to the 1, which is 16. And so we would have 16 in decimal. And so what that means, if we added these up, of course we have the total would be 16 plus 2, so it would be 18. So basically, when you look at hex 1, 2, you're actually looking at decimal 16. And also, the reason we deal with hex and binary, it turns out it's very easy to convert hex to binary, and because you can basically take, let me do this example here. So if we have hex 12, to convert to binary, you basically group everything in groups of 4 1s and 0s. So this, when I look at this 1, I know that would be 0 0 0 1, and then when I look at the 2, it would be 0 0 1 0 if I converted that. So if we take this here, and of course what I did, anywhere I have a hexadecimal digit, I convert it into the binary representation. So here, this is binary 2. Here we have the hex 2, and then this would be hex 1 0. And so here I'm saying this is actually a 1 right there. And so if we converted this, basically this hex 12 is this in binary, and is of course 18 in decimal. So base 10, we have base 2, and of course this was base 16. So let's run a quick code demo here to show you some more examples. Suppose we said for integer I equals 0, I less than, let's say I less than 32, and I plus plus. And each time we go through here, let's say I want to print out the decimal value, and I also want to print out the hexadecimal value. And notice the convention again for printing out a decimal value we know is %d, but if I want to take that same value and print it out as hexadecimal, I use %x. So here I'll print out the value of I basically 2 times. Once I will print it as a decimal, and the other time I'll print it as a hexadecimal. And let me run this. And this is one pay attention to. Make sure when you run it you understand it. It's really cool because you can see how we count here from 0 to 31 in decimal, and then you can also see how we do the same thing in hexadecimal just by looking at the values that are output here. Notice hex goes 0 all the way up to F, and then we've run out of digits, so we have to then start over here, 1. Of course we go all the way up. So definitely between this demonstration and also looking in your book, make sure you understand going from decimal to hex and also to binary. The chapter ends with a comment about negative numbers. And negative numbers, they use something called 2's complement. So negative numbers represented in the computer actually are 2's complements. Let me demonstrate by having an integer. I'll say we have num1 equals, say, 10, or we'll say 6, and let's say integer num2 equals -6. And of course, if we print those out as decimal values, num1 %d and num2 %d \n, and we say print out num1 and num2, really no surprise here, right? I mean, that's as you would expect. The surprise comes when you print these out as hexadecimal values. If I say print the same thing again, but this time I'm going to say let's print these as hex values. So let's print both of these as 0x and 0x. So the one that's surprising, not so much the positive value, but the negative value, when you print it out in hexadecimal, it looks a little different than perhaps you were expecting. And the reason it looks different, this is called 2's complement, and it's the way negative numbers are represented in a computer. They use what's called 2's complement. And 2's complement is easy to do. So 2's complement, if I give you the number -6, to convert it into 2's complement, okay, so to convert to 2's complement, step 1, so step 1, you basically flip all bits. Well, what do I mean by flip all bits? Well, you represent this as binary, and binary 6 is 0, 1, 1, 0. Okay, that's what 6 is in binary, right? In fact, notice right here when we ran our program, here's 6, and 6 in hexadecimal is 6. But if you convert these into 4 digits using 1s and 0s, we have 1 or 0, 1, 1, 0. So what we do to flip the bits, we would say 1, 0, 0, 1, right? We have flipped the bits. So that's step 1. Step 2, you just add 1 bit. And what I mean by that, we would say, okay, let's take this 1001 and let's add 1 more bit right there. Well, when we add that, of course, let's take each one in turn. 1 and 1, we're going to get a 0 here. And because 1 and 1, remember, we can't have the number 2 there, right? We have to carry a 1. So 1 and 1 is actually 1, 0, but we carry the 1. So then we have 1, 0, and then that would be the 1 here, right? Because we had the carry. And then we have the 0 and the 0, so that would put the 0 here. And then finally the 1 here, we just bring it down. And I want you to notice this right here, 1, 0, 1, 0, is actually hex A that we see right there. And the reason you see all these F's, that represents that it is a negative number. So basically all the F it shifts this over, kind of ignore the details, but since we've got an int, in fact, you know what? Let's change this to a char. Let's change this to a char. And again, do a run. I guess it printed it out the same way here. But the sign bit, which in this case is this most significant bit, gets expanded out, and that's why we see all the F's like we see there. Maybe another way to convince you about this, let me make this as int again. Int. And let's just suppose we said num2, actually let's have another one, int num3, and let's say this is equal to FA. Alright, let's say it's equal to FA. In fact, let's say that it's equal to, we'll do it just like we've got here. We'll say it's equal to FFFF FFFA. Okay, so that's 32 bits. This is actually in hexadecimal, the representation of -6. And to prove that to ourselves, we'll do a printf num3 %d\n. And let's also print, we'll print it out as hex, and let's also print it out as decimal. So I'll say print out num3 as hex and print out num3 as decimal, and we click and run that, and notice sure enough we have the hexadecimal representation and the -6, which is again showing the 2's complement. So make sure you understand this video. Also on the quiz you'll have some conversions to do. There's some in your book as well on page 122. Definitely you'll be working a lot with hexadecimal numbers. Computers basically use hex for everything. And of course now you can see hex converts nicely to binary, which is why we use hex and binary in our computers.